So using this, we came up with this whole description of how to look for corner or responses of corners in an image. And we looked at this diagram, and again, basically this is showing you in the two different eigenvalues that if the eigenvalue 1 is larger and the eigenvalue 2 is smaller, this is the kind of a shape you get. If both of them smaller, this is what you get. If eigenvalue second one is larger, this is the shape you get. And of course, when both of them are larger, this is the shape you get. Of course, this is the corner. So we're looking for mostly corners. This would be an edge, this would be an edge, and this would just be a thresholded point. We also looked at details of how we can actually now, just if we know the second moment matrix, we can actually compute all of this straight from the second moment matrix, and we actually look at determinant of this matrix and trace, and actually just comes out to this simple calculation, and we use a small weight factor constant to help us do this calculation. So if you notice here, R, which basically is giving us this information about what is a corner or not, is only dependent on the eigenvalues of the second moment matrix, making it larger when it's a corner, negative with large magnitude for an edge, and small, or the magnitude of the R would be small, and that's where this region would be. So again, we can do all of this without any explicit computations of the eigenvalues because we know how to compute the M straight from the image by just doing the derivatives and then using the gradient computation to help us get there, which actually is an efficient way of doing these kinds of things. And again, this is one of the reasons this kind of stuff can be done quite efficiently in most simple computers. Again, remember, this was the equation that now we just have to compute, and we can actually do this on a neighborhood with just image intensities and the derivatives of image intensities.